Finally, distribution of indistinguishable objects into indistinguishable boxes, as I said, boils down to the integer partitioning problem. A partition of a positive integer n is a way of writing n as sum of positive integers. For instance, 6 is equal to 1 plus 1 plus 1 plus 1 plus 1 plus 1. This is one way to write 6. But it's also equal to 2 plus 1 plus 3. Or it's equal to 4 plus 1 plus 1. Okay? So these are all distinct partitions, but for instance, 1 plus 4 plus 1 is not a new partition because here we do not care about the order. If you just swap the summands around, it's not a new partition. Okay? Two sums that differ only in the order of their summands are considered the same partition. So this one and this one are different, but this one and this one are the same. You see, my elements here are just ones. There are n of them. I have n ones, and I would like to partition them into subsets, but the ones, they are the same. In the earlier questions, they were different because they were elements of a set, but now here, they are just ones. They are all the same. And here I'm going to, I would like to obtain the partitions. And the concept of order is now non-existent. Now, this is the integer partitioning problem. So the question for 6, for instance, how many ways are there I can write 6 as sum of positive integers, right? 1, 1, 1, 1, 1, 1 is 1, for instance. 1, 1, 1 plus 1 plus 1 plus 2. Or 1 plus 1 plus 1 plus 3. Or 1 plus 1 plus 4. And it goes on like that. So how many ways are there to do this? The partition function P of n, representing the number of possible partitions of a non-negative integer n, satisfies this recurrence relation. Of course, P of 0 is 1 because there is only one way to express 0, and this is not a positive integer anyway, but we just treat this as the empty sum, okay? So empty sum is 1, therefore we say that the partition function of 0 is 1. Well, P of 1 is also 1, okay, but usually the base case is start from 0, and P of n is equal to this expression here. This is related to what is called the pentagon numbers. If you are interested, you can look this up. An interesting concept, and turns out to be equal to this infinite sum expression. And this actually, the partition function also satisfies this identity where this infinite sum equals this function, and in fact this recurrence relation is a result of this identity, which I'm not going to go into, where this function is quite a famous function called the Euler Function, of course laid out, named after Euler, and it's quite important in a lot of problems. It arises in a lot of applications. The issue with this is we do not have any closed form expression for this function. Okay, so we cannot express it as just a single formula. Either you have to apply this recurrence relation or this recursive definition to come up with the exact value that you need, or sometimes we use what we call generating function methods, which we'll talk about later, to obtain the value of this function.